Yeah. Okay, very nice, everyone. So today we have Lex Kemper that as our speaker at the colloquium at PUC. So I know Lex since, let's count it, I think 15 years, right? More than that.
At least, yeah.
So since we both were graduate students at the University of Florida and studying with the same supervisor. Although unfortunately, I never got a published paper with Lex yet.
We'll fix it.
And but I saw him that I can say that I know quite well his research line up to the time that I graduated. So actually, I'm a little bit more senior than him. So Lex did a lot of works in high temperature superconductivity as myself, and then at the time that we were both in the graduate school, that iron pnictides and other big classes of high TC superconductors were discovered. So we jumped into this field and published a lot of papers. And then he also worked a lot on the this kind of pump probe type of experiments, which means that you shine the laser to try to excite the superconductors or whatever into a excited state, right? And then studying the dynamics of the systems. And also Lex did postdoc in Stanford, and then also later in Berkeley, right? I think you also, during this time, you still work a lot on this kind of pump probe problems.
Yeah.
Right? But today you can see that Lex is gonna tell us about a completely different subject. Like I should say it's probably a new interest that he has over probably the past few years, right? And that I don't know too much about. But I should comment that I remember Lex since he was a graduate student. He's highly interested in numerical calculations, right?
Uh-oh.
And this kind of, let's say, more technical.
I think we're
to us this subject that you are going to be talking about. So please go ahead.
All right. Thank you.
I might.
Yeah, you were a little in and out a moment ago, but I think you're back. Or is it me? Can you guys all see this? This is okay?
Yes.
Okay.
Yes.
Okay. Thank you, guys. All right. Wei, thank you for the lovely introduction. It's nice to see you all on the screen. Normally, I say that I am very sad that I don't get to visit in person. I think this is particularly true today, given that it would be nice to visit Rio, but that won't be today. So we'll do it online. So today I'll be telling you a little bit about solving some problems in condensed matter physics and how you do that using quantum computers. Okay. The most important thing that I should do is I should acknowledge all the people that have worked on this with me. At NC State, there's some undergrads and some graduate students, and then I've got some lovely collaborations at Georgetown. I'll have some experimental results from the quantum computers at the University of Maryland, and I have some collaborators at the company IonQ. Okay. At any given point during the talk, if you have questions, please feel free to ask, feel free to interrupt. I have the chat window open, so you can also do some things in there. And there'll be at least one point where I'll ask you to participate a little bit, and we'll do that via chat as well. Okay. This is the outline. I realize it's a lot. We may not get through all of it. That's okay. The idea is to sort of give you a brief introduction to what quantum computers or what quantum computing is for physicists, right? Why we might care. A very simple example that everybody that's taken a basic quantum mechanics class should be able to follow along with, and then to do some of our fancy things that we've been working on lately. Okay. So the idea of simulating physics with computers is not new. It's been around for a very long time. The idea of simulating physics with a quantum computer is a little bit newer, but still relatively old. This is the very first work on that came out of a conference that Richard Feynman was attending, where, among the other things, they were wondering, can you simulate physics with computers, and can you simulate them with quantum computers? And what they meant by that point is really a quantum system that is sufficiently cleanly controlled that you can make it look like other quantum things that you care about. So, problem one, can classical physics be simulated by a classical computer? Yes, we can do this. Sometimes it's hard. Predicting the weather is still difficult, but in principle, we could do it. Quantum simulated physics can also be simulated, but as we'll see, runs into some issues. And so 3 or 4 are the sort of new things that we'll talk about. Okay. So why do any of this for condensed matter? Well, this is part of a screenshot from my website from a few years ago at this point. It says quantum materials in and out of equilibrium. And so this is what Wei was talking about. Is one of the things that I do is I study what you get when you take quantum materials and you drive them with pump probe experiments. What that means is that you work together with folks at facilities like this, the LINAC coherent light source that sits at Stanford that produces high intensity, ultra fast X-ray beams. And the thing that you can do with that is you can take essentially movies of what the electrons and what the atoms are doing at their internal timescales. So atoms, they move at femtosecond, picosecond timescales, and to be able to see that, you have to work with these sorts of experiments. It typically look like this. I have some material. It'll start again in a second. I excite it with a pump beam, red laser. Everything goes and wiggles, and at some point later, I draw out some electrons and I measure those. And by doing that, I can take static experimental pictures like this, and I can turn them into fully animated. These are the dynamics of my system as I've driven it out of equilibrium kind of stuff. This is really impressive experimental work. Now, from a theory end, right, how do we do these, complicated quantum problems and try and do them in the time domain? Well, we do a lot of numerics. So we can do some non-equilibrium Green's functions. That's what I have on the left. We've done a bunch of work on that. You can do density matrix normalization in the time domain. That also works for some period of time. You can do essentially exact diagonalization. So you write down your problem, you put it on a computer, you diagonalize the whole thing. In either case, it will take one of these things up here. This is the Cori supercomputer, and this is the Summit supercomputer. The problem is that all of these methods, all 3 of these and all the other ones, eventually they run out of gas. They reach some kind of computational barrier, whether it be memory or I just can't run my calculation long enough or my algorithms don't converge. They all reach a barrier and we have to do something else. This is where quantum computing is supposed to help. So if your newsfeed looks anything like mine on your phone, there's a lot of quantum computing these days. There are a lot of companies in this space. This slide is now a year old. It's out of date, but even if I made one today, it would probably be out of date tomorrow, because there's a lot of companies that live in this space. And the reason being is that, the community has sort of decided that rather than this being a fundamental physics problem, it's an engineering problem. So that means, if I pay enough engineers and I throw enough money at this problem, we can come up with good quantum computers. There are several hardware platforms that people are using. They are all quantum computers of some type or another. D-Wave is slightly different, but all the other ones they are all essentially the same in that what I need is I need a 2-level system, some kind of quantum system that has 2 levels. Now, there are tons of those, right? So I could do spins, right? Spin halves have an up and a down. I can do trapped ions, and I can access their various spin states. We can do different kinds of neutral atoms. Superconducting qubits are essentially nonlinear oscillators, and so you can pick 2 levels that the spacing of very well, and that's your 2-level system. But really, any 2-level system will do. And this is what you build quantum computers out of. So I thought I should tell you a little bit about what it is. What is it good for and how it works? I'm not going to talk about how we make them because that's a whole separate talk. But rather than tell you immediately what it is, I'll tell you what it isn't. It's not a supercomputer. So it's not as if you have, let me take my laptop and let me take 5,000 of them and wire them all together. It's not a cloud computer. In other words, 5,000 laptops that sit in a different building from me. Nor is it a better version of your current computer. So it's not like we're going to take this this device here, which is the first computer I ever used, and just make it better by making it quantum. That's not how it works. Instead, what they do is they answer a different type of problem very well. And they answer types of problems that are difficult for classical computers to do. So I'll illustrate this by an example. And it's sort of a simple one. On the left is a building that my office is in, not today, but the other day. And on the right is same thing, the thing behind me, this is the library on campus. And I could ask the question, how do I get from place 1 to place 2? Well, okay, I can draw a map, a schematic map of what things look like. There's my office, there's the Hunt library. And I can walk along, and at some point I will have to make a decision. I will have to either turn or I will have to continue straight. Right? So that is effectively one bit of information, one yes/no question. You can call it turn or continue straight, or true or false, or 1 or 0, but it's all the same. It's a binary type of choice. Based on binary kind of things, you can do classical computing with gates. There are truth tables, there are all these sorts of things, and that eventually lead you to a computer. And in fact, I can ask a regular computer, how do I get from my office to Hunt library? And I will ask Google, and Google will tell me you should walk this way. Okay, good. How did it decide that? Because when you think about it, there's a lot of options, right? Like I could have gone straight, but also I could have walked over this way and gone through the park and then gone around, right? So let's think a little bit about how much information this sort of thing contains if you were to try all of the possible combinations. All right, so if I have 1 turn, then I have really only 2 options, 1 or 2. If I have 2 turns, well, I could turn twice. I could turn once, continue straight. I could continue straight and turn, or I could both times continue straight. That builds, and it gets bigger, and it gets bigger. So suppose, just for sake of argument, I have 50 turns to make. How many possible paths does this give me? How many things, if I were to do this with a classic computer, how many different things would I have to try? And you all get to answer this. So take a second, think about it, and put your answer in chat. Go. Don't worry, I'm not going to grade it. I think everybody's asleep. There's one. All right, 1 answer. Anybody else? C. We have 1 D, we have 1 C. Good. More guesses. I like it. I'll wait for 1 more. More than 10 to the 30. Okay, good. Well, thank you for engaging. There's the answer. I don't even know how to read this number. It is a very, very large number, right? So, and that's just for a simple question, right? Like, how do I get from one place to another? The answer to, how Google decides this is it obviously doesn't try all of them, because if it did, it would take longer than the age of the universe to try all of these possible combinations. And so it's got heuristic algorithms. Now this maps onto physics problems in the following way. These 50 turns also map onto, well, if I have 50 possible spin 1/2, how many arrangements are there? And that's the same number. And so answering these kinds of questions where you have an incredibly large search space, or in this case, an incredibly large Hilbert space, right? That's how many complex numbers you would have to store. These are the kinds of things that quantum computers are good at. And this is why we're intending to try and use them for quantum mechanics kinds of problems, because Hilbert space is sort of unreasonably large. It does so by leveraging 2 different aspects of quantum mechanics. Superposition, right? So I can take my yes and no, my 1 and 0, and I can make some combination of that. So I can make a wave function that is a combination of that with some arbitrary coefficients. If you remember your quantum mechanics class, this is also like a spin on a Bloch sphere with 2 possible angles. You may have seen this in your textbook at some point. So it uses superposition. That by itself is not enough. It also uses entanglement. So things we can do is we can take 2 qubits. We can put them through a quantum little machine called a quantum circuit, and I'll tell you a little bit about how those work, and produce a state that is not factorizable into one state times another state. This is called entanglements, and this is the other sort of critical aspect of quantum computers, and that's what we're going. These 2 things are what we're going to end up using. Okay. All right. So we'll start with a simple example, and we'll talk about spin waves in the ferromagnet. Any questions before I go on?
No, I think it's pretty clear. So,
all right. Okay. So the reason we were looking at this from a condensed matter physics perspective is that spin waves are low energy excitations. So low energy excitations and correlation functions are how we think about all materials, right? Mathematically, you would write it as if I apply some operator B at R prime and T prime, what do I get in R and T? Really what you can think about as well, perturb this material here, and I'm going to look here and see what I see at that point. And it tells me about the internal dynamics of the system. And this is what you do when you measure conductivity, when you measure spin-spin correlation functions, when you measure RPEs in some regard. All experimental measurements are done in this way. You perturb your system and you look somewhere else. So the system we were playing with is the Heisenberg model, a bunch of spins in the ferromagnetic kind. In the ground state, they all like to point up, they all like to arrange, because in that way they minimize their energy. If I make all of these are neighbor spin interactions, and if I make all of these line up, then I have the minimal energy. Now you can think about the excitations that you get out of this system, or that you can make. A simple excitation out of the ground state is this. It turns out that is a high energy excitation, and it's not the lowest lying one you can make. The lowest lying one you can make for this kind of a model are called magnons. And so these are small modifications of the spin, and they look like little spin waves as you go around. You can compute what their dispersion is, but you can also go and measure this. And this is something that you can measure with neutron scattering. And so this tells you about the underlying dynamics of your system. Because, for example, if I had an Ising model or an Ising material or Ising, it wouldn't look like this. I would see something else. So excitation spectra are important. All right, so how do we map this onto a quantum computer? Well, the idea is as follows. You build what's called a quantum circuit. It looks like this. It's sort of dense if you don't know what you're looking at. So let me talk you through what these are. I have 2 parts of my system, of my quantum program, if you like. Down here, I've got my system qubits. In other words, however many spins I'm looking at, that's how many qubits I'm going to have. Spins are a very nice thing to look at with a quantum computer because they're already 2-level systems. I don't have to do anything further to make them match onto this. Here is an additional qubit. It's called the ancilla. And what we're going to use it for is we're going to use it to actually perform our measurements, to measure our correlation function. All of these things are different kinds of quantum gates, some of them composite, some of them sort of native ones. What this thing does is it produces a 0 + 1 and makes it into a superposition. This thing makes the ground state of my system. How that does that, we can talk about it somewhat detailed, but for a ferromagnet, it's very straightforward. And then the idea is that you entangle your ancilla with your system by this A operator, depending on what the ancilla is. You let it time evolve, you apply your B operator with that, and then you make a measurement at the end. So your typical quantum circuits look like this. Even if they're doing something else entirely, they typically look like prepare some ground state, do some time evolution, apply some operator, and do some measurements. Okay, so let's see what we get. So the first thing we tried was to try this for 2 qubits or 2 spins. This is a very straightforward system. We know what all the eigenstates are, right? We have a triplet and we have a singlet. And so we looked at what the excitations are. So there are two kinds you can make. You can perturb one spin and look at what it does. You can perturb one spin and look what the other one does. There's only one energy scale in this problem, which is the difference between triplets and singlets. And so you get oscillations at exactly that frequency. The solid lines are what you expect from a pen and paper calculation. And the dots are what you get if you run this now on a quantum computer in 2019, I think. All right, we do this circuit on the left, we implement all the various pieces, and you run, this is what you get. So we thought this was pretty good, actually. It's like, okay, great. So let's try 4 spins. If 2 works, let's try 4. And so you do that. Now you have more energy scales, and so you get more complicated oscillations. There are 3 different kinds of things you can measure. That's all fine. When you run this on a quantum computer, this is what you get. It's not nearly as nice, right? This is a much more messy kind of result from your experimental equipment. So not sad trombone, not great. It turns out that you can pull some information out of this. You can Fourier transform it. You can do a variety of things. So you can get something that looks like a Magnon dispersion with some leakage between channels. So the right frequencies are in there, even if they're hard to get out and even if they're incredibly noisy. And this sort of illustrates the state of quantum computing today. We have quantum computers, they work, but they're incredibly noisy. And a lot of effort is being spent in how do you take this noisy result and still get some useful physics or some useful result out of it. Well, it's more than that. This was only 5 qubits, 4 plus my ancilla. That's a Hilbert space of 32. And I could probably do that on my watch, right? Like, these are not complicated calculations. So that's the other point about quantum computing today, is they're not really in a state where they're going to do better than classical computing anytime probably soon. So part of the game is, how do we make use of them anyway? And how do we come up with new things that you can do with them, such that if in 5 or 10 years we have new quantum computers and better ones, we'll be ready to do something with them. And the other perspective is, maybe we can take some of the ideas from quantum computing and bring them back to the classical world and think about new ways of calculating things. Okay, good. So there are 2 things that I wanted to tell you about. I wanted to give you all a chance to ask questions first, if there are any.
Okay, maybe I should ask a question, because I'm not quite sure what you mean by noise. I mean, in the previous slide.
Yep.
This okay. Well, first of all, these lines are okay. The real part and imaginary part of correlation functions, and then the dotted ones are you are using the quantum computers to simulate this thing.
Yes.
But how exactly? They are plotted as a function of time, right?
Yes.
Yeah, but how do you do this exactly? Like,
so essentially, this is the circuit that we run, and this circuit effectively implements the Lehmann representation for an operator, right? So for a correlation function, you apply some operator, you time evolve it, and then you measure the other operator.
Oh, okay.
Because you can't measure wave function phases, you have to do this with this additional ancilla, but that's the basic idea.
But where does the noise come from?
The noise comes from a variety of places. So one, I take my qubit and I do something with it, and then I have to wait. And while it's sitting there, it's going to decay back into its ground state. So qubits naturally, once they're not in their 0 state, have some decay time, have some decoherence or population decay rate back to their 0 states. So that's the first problem. The second problem is that any gates that I apply or any quantum operation that I do is not 100% accurate. On a good day, the sort of gates that we care about are maybe 92% accurate. So if I apply one of these, I'm 8% wrong. If I apply two of these, I'm 8² wrong. So it starts to add up quickly. And so realistically, you're limited to, maybe 50 of these gates of these quantum operations that you can do before your system, because before it does not represent at all what you had intended anymore. So those are the two major sources of noise.
I see. Okay.
Can I ask a question also?
Yeah.
Lex, was that with Qiskit or?
Yes, this was run with Qiskit on the IBM quantum computers. Yes.
Okay, thanks.
If you run this today, it'll look better, actually. Not amazingly better, but it'll look better today.
Yeah, no, because I also ran some stuff with a student 2 years ago, and it was basically noon states, and you do n equal 2 and then equal 3, and by the time you get to 4, it's already quite similar to get there. It's
yeah, exactly. So it's gotten better, but not incredible.
Sure. Thanks.
Yeah. Okay. So, any more questions? All right. So we'll tell you about thermodynamics a little bit. So let's see. So first, why thermodynamics? Well, because we're condensed matter physicists and we care about phase transitions, right? And finite temperature physics and all these sorts of interesting things. And there's a variety of phase diagrams that I have here. One for the materials that Wei and I worked on, the pnictides. This is a manganite, which has, I don't even know how many phases on here. And so we really want to eventually push in the direction of being able to study these things, and not just at 0 temperature, but also at finite temperature. So we care about these things. To sort of fix a picture in your head of how we're going to go about doing this, right? So let me take a simple Ising model. What we know that this does is if I increase temperature, or rather if I decrease temperature, I go from some disordered thing to what is effectively a magnet. It's got a melting point somewhere, or an ice point. If I apply a magnetic field, the phase diagram gets slightly more complicated, but this is a simple sort of model that you may have run across in your courses. So how do we deal with this? How do we think about this? Well, what you also learned in your thermodynamics class is that to consider these kinds of things, one should think about the free energy. At low temperatures, the energy wins, and so I am dominated by this sort of kind of thing. At high temperatures, entropy is preferred to minimize the free energy, and so I end up with this. The entropy is given by a trace of a density matrix, and this is where the problem comes in to put this on a quantum computer. Why? Well, density matrices are, unless you are at 0 temperature, these represent mixed states. Quantum computers, that they work with pure states. There tend to be typical wave functions. Second problem is that if you have to go and measure this density matrix, it requires a lot of measurements to do that. It requires some exponentially large number of measurements. And if you have to go and do that, that makes the whole point of having a quantum computer go away, because you'll have one, but you will have to do so many measurements that effectively you might as well compute it classically. So these were ways that we had to get around. So we got around this particular way of computing the entropy, rho log rho, by going through the partition function. Okay. Of course, you all know this, but I will remind you, this is the partition function. It is a trace of e to the minus beta h, or maybe it's more familiar if you look at it like this. It's the sum over all my eigenstates weighted by e to the minus beta. It's an interesting object. You can think of it like a generating function that gets you all your thermodynamic things. You can think of it like a normalization factor. It's got a bunch of ways that you can think about it. And today I'll be telling you about a different one. What does this thing look like? Well, let's take our classical Ising model again. Here's my phase diagram. If I compute the partition function for, say, 100 sites or so, it looks like this. Here's my applied magnetic field, and here's my temperature. And you can see that it's got something that happens right around the phase transition. It's not precisely sharp like this is because I have 100 sites and not infinity of them. The free energy is the log of this, and you can see that it already has, all sorts of interesting things going on as you start to cross this line, and that tells you about susceptibilities, heat capacities, these kinds of things. Okay. So let's think of the partition function in a different way. Right, here it is. I have it again. Z is e to the sum on exponentials. Let's think of it as a function on my parameters. Yeah, so my parameters in my Hamiltonian are j and h. I will set j to 1. So it's just h and it's beta. Those are the things that essentially control what my function looks like. So let's think of it literally as this word, a function on those parameters. As long as I don't have infinity states, it's a nice function. It's a sum on exponentials. So it's positive. I can take as many derivatives as I want. It doesn't diverge, all of these things. Right, because it's a trace of exponentials. That means I can do Taylor series. I can do a polynomial expansion in either variable. Let me pick h. We also know from the fundamental theorem of algebra that every polynomial can be entirely characterized by its zeros, meaning I can take any polynomial. Here I have a cubic one, and I can factor it. For z, the partition function is positive definite for normal values of beta and h, for real values. It nevertheless must have zeros. Thus, the zeros must lie somewhere in a complex plane. Same thing as if you have this kind of a polynomial from your algebra class, you can still factor it, right? You can do the quadratic equation and you end up with complex numbers. That's because the roots of this polynomial lie somewhere in a complex plane. And so that's what we're going to look for. This is not a new idea. This is an old idea, originally proposed by Li and Yang when it's done in the magnetic field. And thus these are called Liang zeros. They tell you all sorts of interesting things. If you look at the patterns of the zeros, as you go across a phase transition and you plot what they look like, here I don't have the zeros, I have the exponential of the zeros. Below the phase transition, they sort of pinch the real axis, and above there's this gap that lies in my physical range of parameters. So, and by analyzing how they move, they can tell you about phase transitions, they tell you about the order of the phase transition. You can get some idea of critical exponents if you look at the density of zeros. Because these are poles in the free energy, they tell you about radius of conversion of thermodynamic expansions. They contain a whole lot of information. This was known, and what was interesting lately, and the reason this viewpoint in physics was written, was that they were measured experimentally. So this was following a proposal by Bobo Wei, and then some experiments in a group of Renbao Liu, who did the following. They took I have to look this up, trimethyl phosphite, which has these orange ones act as 9 free little spins. And this blue one, which is a phosphorus ion, is also an NMR active. And what you can do is you can treat these 9 little ones as spins in your system. You can treat the phosphorus ion as a measurement device, as an ancilla, which is what we're going to do. And essentially, by letting this time evolve under its natural interaction Hamiltonian, you can then pick up what the zeros are. And I'll tell you a bit more about that in a second. So they measure this experimentally. What caught my eye was this structure, because this is essentially already a quantum circuit, right? We prepare an initial state, we do some things with it, and then we measure the ancilla. And boy, that looks a lot like the kind of things that I was just showing you for the spin-spin correlation function. So we decided, let's take this idea and we'll implement this on the quantum computer. The model we were looking at is the XXZ model. It is a spin model with slightly more complicated. For this value j equals 0, I just have my Ising model again. If j goes much, much larger than jz, then this is an XY model. You can sort of very easily on pen and paper compute what the zeros look like. For the Ising model, they have to be complex, right? They have to be imaginary. So they lie, in fact, on a pure imaginary axis. And if you take the exponential of that, you get this sort of circular shape, right? Because the exponential of a complex number is just a unit circle. On the XY side, they're still complex, they have to be, but they look really, really different, right? Here they lie on the vertical axis, here they lie along the horizontal axis, shifted. And so the thought was, okay, well, quantum computers are not very good, but if I have to tell the difference between this kind of thing and this kind of thing, that's a qualitative difference. I don't have to look at numbers. I might just be able to look at this and say, oh, these clearly look different. So even with a bad quantum computer, I should still be able to identify this phase transition. So that's the idea. So we have to do a couple of things. We have to prepare a thermal state. There are solutions to that. And we have to figure out how to do time evolution under the complex field. That's also doable. So we built some circuits for this. I'm happy to tell you more in detail, but I think this is not the right place for it. But it's again got the same sort of structure. I build a state, I have an ancilla that I put in superposition, I entangle it with my system, and then I measure my coherence. It's the same sort of idea. In this case, because we want a mixed, what we have to do is we have to build this dilation as a pure state. But there are sort of standard ways of doing that. Okay, so here's what you get. So here's my model again. Here's my XXE model. Ising-like on one side and XY-like on the other side. I'll remind you, this is what the zeros look like. Imaginary part, here they lie along the imaginary axis, here they lie along the real axis, but shifted. And here's some results from a real quantum computer. Because again, the limitations in number of qubits, we're able to do this for a two-side system only. And here is the measurement ancilla as a function of time, or if you like, as a function of imaginary field. That's the axis here. For the Ising-like case, the imaginary part is supposed to be identically zero. Quantum computer, we get something that is basically zero plus some noise. For the real part, it's supposed to cross down here. The quantum computer results tell me it crosses down here. But not too bad, actually. This is not from IBM's machines. This is a trapped ion computer in the lab of Norbert Linke at Maryland. On the XY side, the pattern looks very different. And this is what I mentioned, right? Like it's qualitatively different. And so without even having to measure precisely, I can tell you these two things look different. So that's useful. The imaginary part always has this pattern. The real part always has this pattern. And it sort of depends where you measure in the real axis, whether you pick up these zeros. Okay. So we can now take this and do this as a function of J and look where we find the phase transition. This is the data I just showed you. This is for the in-plane J is slightly less. So it starts to move towards the phase transition. These zeros that sat here now shift closer towards pi/2. Here's where COVID happened and all the labs shut down. So we don't have any data at these points. Luckily, we do have data for the endpoints, and the zeros indeed, so this is from simulators, they do shift from this horizontal, from lying along the imaginary axis to lying along the real axis. So we really pick up this quantum phase transition with the quantum computer. As promised, once we have the partition function, we can do all the things that we want. And in this case, what we did is we reconstructed the free imagery. So even with relatively noisy data, we're able to identify where the zeros were and pick up what the free energy should be at those values of J. So this is a way that you can get at thermodynamics. And not only that, you can take this idea of partition function zeros, which has kind of been buried for a little bit. And I think this could be useful for classical computing as well. Okay. Let me pause for any questions and have some coffee before I move on to the next topic.
So your claim is that even if you have a noise, this from the pattern you can still tell the phase transition. Is that
yeah?
Okay. But is it possible that the noise is so large that
yes.
watch out this pattern?
Yes.
But
if
then
you try,
how many times have you? I mean, these experimental lines. How many times you have done the performance, or is it an average over several?
Yep.
rounds of experiments, or
It is a quantum experiment, and every time you make a measurement, it picks out a point, and so you always have to do a couple thousand measurements to build up statistics. So these are on the order of 1,000 measurements, I think.
which you can still argue that this is cheaper than running a classical computer.
Oh no, not with 5 qubits. Right. This again, this will run on my watch. Right, but the idea is, certain points I might be able to treat 50 spins. 50 spins I won't be able to do on a classical computer anymore, but this technique will still work.
But still, this would rely on the fact that you have very different patterns for these zeros, right? But
yes.
Is this generally true for any phase transition?
No, not all, but many of them.
Okay.
Yeah.
I mean, is there some situation where the phase transition, let's say, for instance, the phase transition happens, but everything still falls on the line that?
Yeah, already in this case, the anti-ferromagnetic case for the X-Fi model, it doesn't do the same. It behaves different, and it's not quite as nice. There you may have to look at, so these are zeros in applied magnetic field, but you can compute zeros in any parameter, including temperature. And there you have to look at the ones in temperature. So those are called Fisher zeros. So you can or you could do, you can apply this for staggered magnetization. You can apply a staggered field. So there's ways around it.
I see. So
to answer your other question. Sorry, go ahead.
So your statement is more like, if the pattern of zero changes, then it should be robust against decoherence or something like that. No.
See, yes, but to a point. If I try and run this on IBM, it won't fly. I won't data. I'll just get random noise.
Yeah. Okay.
It's too deep of a circuit, and as I mentioned earlier, too many gates means everything decoheres and goes away, and then you can't do anything anymore. So there's always a point where you have so much noise that you can't pick up anything anymore.
Okay, can I ask a quick question?
Yeah.
You said you programmed the thermal field double, right?
Yes.
The state.
Yes.
So if instead I make a quantum circuit, which already has the interactions of the Hamiltonian that you are interested in, built inside there physically, and it's a noisy circuit, so it decoheres anyway, I'm going to get a thermal state with the density matrix given by the Hamiltonian that you target, right? And
I think you get
so it's
yes, but noise to push you towards an infinite temperature state.
Okay. That's a problem.
Yeah, it is. So we tried this on IBM, and even producing the density matrix worked okay for high temperatures when everything is occupied, but you try and do this for low temperatures and it doesn't work anymore.
But if if you relax the need for programmability, maybe you can.
Yeah. No, and I think there's work on that, right? There's work on trying to say, okay, well, let me just use the inherent Hamiltonian of my system and try and produce that in that version. Yes, absolutely.
Okay, thanks.
Yes. Okay. So the last thing I'll tell you about, and again, just these are all sort of little vignettes of things you can do, is how you look at some topological physics. Thinking about topological matters has very much revolutionized how we do and how we think about condensed matter physics. The very first strong example of this was in Hall conductance plateaus back in the 1980s, where we found that Hall conductors appeared at quantized levels, quantized multiples of the quantum of conductance. Nowadays, we understand that this is due to topological changes in your wave function. The Nobel Prize in 2016 was awarded for this, for effectively a lot of foundational work in connecting the topology of your wave functions to experimental observables. Okay. Now we thought what's nice about topological things is that they come with integers, right? I have integer multiples of something. And so that means that if I try and look for a topological phase transition or something on a quantum computer, I don't have to look for continuous changes. I can look for sharp step changes as this integer changes from 0 to 1. So in the same way that you can see here, these are sort of step changes all somewhat smoothed out. So that's what we were looking for. And we've done a variety of things. The one that works best is by measuring curvature. And so I'll tell you how we do that. And to do that, I have to talk about this. This is the Earth. And as far as we know, the Earth is round. Yes. How can we tell? Well, one of the fundamental ways that you can tell is by looking at triangles. So we know from the intro geometry that if I add triangles up and the angles in a triangle up, I must get 180. This is true unless you're on a curved space. And that's how you can tell that you're on a curved space. The triangles don't add up to 180. So if I run in a triangle on the Earth in this way, I will get a sum on the angles that is different than 180. Right here, I would get 90 and 90 and 90. So I would get 270. The other way that you can tell is by taking vectors and moving them around and seeing change. That's called parallel transport. So you can take a vector and you can move it around your curved space. And what you can do is you can take your derivative of your vector along your path, and that tells you something about the shape of the space that you're on. So if you make a loop, you may end up pointing a different way than you started. So this is called the holonomy of the space, and that's what we're going to measure. So to move this to condensed matter physics, we don't work on the Earth. We work on two-dimensional, typically Brillouin zones that are periodic, sort of connected like Pac-Man. And so the shape for that is a torus. The equivalent of a parallel transport derivative looks like this. It's the change in the wave function. It's the expectation value of the change of the wave function. And so the question of, what kind of topological phase am I in can be mapped onto the following. If you walk around a closed loop on this torus, so this one or this one, what phase do you pick up? It has to be a multiple of 2 pi because my wave function had better be single valued, but it could be 0 or it could be some integer multiple of 2 pi. And that integer is called the Chern number. Okay. The curvature that's associated with it is called the Berry curvature, and so that's what we want to compute. So we want to compute the Berry curvature. You can do a little bit of math, and what you can do is you can write this as the wave function phase overlap. So you take your wave function at some point theta, you take it at some point theta plus delta theta, you take the inner product, and you look at what the phase is. That's what the log does. How you do this with quantum circuits is same as before. You prepare psi of theta, you evolve it to psi of theta plus delta theta, and with an ancilla, you measure what this overlap is. Okay. I will skip some details of how you do that. All right. So what we looked at is we looked at a chiral-P superconductor, not for any particular reason other than the fact that it has a very nice, clean topological phase transition, depending on what the parameters are. If you look at it's a 2x2 Hamiltonian, and if you look at the way the vector points at different points in the Brillouin zone, and you can plot that, so you can find a trivial phase where everything sort of points the same direction, and you can find the topologically non-trivial phase. And what you can see is already that as I take certain lines of the Brillouin zone, my vector will turn around and pick up a phase of 2 pi. Going and measuring it in the way that I just described gets you the following. So this line is what you should get. These circles are what you get is if you measure the wave function overlap around a path, or more correctly, you compute the Berry curvature across the Brillouin zone on a quantum computer using a circuit that I just showed. And here, really, you can see that topological physics really helps you because I find a Chern number of 0, or I find one of -1, or I find one of +1, and I don't find some random number in between, which tends to be the case when you do calculations of some other inexact things. So as far as we know, this is the first exact measurement on quantum hardware. The reason that works is that this is the kind of thing that we want to compute. Rather than looking at individual bonds, which is what these are, right? An overlap between K and K plus delta K. So in your Billiman zone, that sits there. What we do is we compute the curl. And so that sits around this little plaquette. And what happens is if you pick up some error here from this bond that you compute, it'll cancel when you look at the neighboring plaquette. From a topological perspective, this is the same as being insensitive to local deformations. Your manifold is insensitive to that. And this is why you get an exact result. Now, as Maya was asking earlier, eventually you get enough noise that this doesn't work anymore. What we did is we built a fake quantum computer hardware in our computer, excuse me, and increased the noise until the number of times we got it wrong was above 0. So here we always get the right Chern number, and as you increase above some certain noise floor, eventually you end up with garbage. It doesn't work anymore. Okay. So the last thing I wanted to say is to sort of advertise, how we can think about quantum computers as functioning physicists, right? Ideally, what we would like is we would like to have some kind of quantum software stack where we take our physics input, whatever it is, compute all of these, work with all of these things within my quantum computer, compute ground states, do time evolution, build thermal states, and build some observables. And this is where the quantum computer is supposed to take over for our pen and paper work in our classical computing work. And so this is where we've been working to figure out how precisely you do this. Okay. Thank you for your time and thank you for your attention. I'm happy to answer any questions you have.
Okay, thank you very much. Very nice talk. Yeah, I like this very nice introduction that everybody seemed to be able to understand. So I have a few, but I think I kind of missed the very last part that you're talking about. So first of all, what you mean by Berry curvature is actually Berry connection, correct?
So yes, we're computing the curl of the Berry connection, curl of the Berry curvature, thus the Berry connection. Yes.
Okay, but okay, I was gonna ask you how you're gonna deal with the gauge invariance. But I guess you don't have this problem, right?
Yep, we don't have this problem.
And then just this slide, can you say again what exactly are you doing? You're measuring it on the Toronto computer. That's many times. And then you're trying to get this topological invariant, which is always integer, yes, regardless the noise, right?
Yes. Yes.
And then, sorry, the slide before. So can you go back to this slide?
Yep. This one.
Yes, and this is what does this mean?
Okay. So this is what we measure. We measure wave function overlap. We compute the curl, or more correctly, the log of the curl.
Oh, right. So this 4 arrows means the way of measuring Berry curvature, essentially, right?
Yeah. So we take the overlap. This is the thing. The raw data that we measure. This is post processing. This is what we calculate with it. And so for each plaquette, we get this value for f. Yep. Now, what's nice about that, when I measure this bond, I might get the wrong answer. I will get the wrong answer by a little bit because my quantum computer is noisy. So it will introduce an error, but the error it introduces comes with a positive sign here and a negative sign here. And so when I sum my Berry connection over the entire Billiman zone, excuse me, those errors will cancel.
Well, then wouldn't you just effectively measure the boundary anyway? Or
you can, but if you only measure effectively, you are only measuring the boundary. Yes, but you need to measure each individual point to be able to get the errors to cancel.
But why don't you then just measure the whole boundary without doing this little loops?
So you mean why don't I go and make loops around this way?
Yeah, for instance.
You can do that. If you make a loop here, you might get some errors that go along this direction and you don't pick that up. So that we've done. Find you the results if I can find the appropriate slide. Oh, I guess I don't have it in this talk. I'm sorry. You don't get, so that's measuring the Zach phase go around. And that is not as precise. You see something that jumps, that goes around, but it's a lot noisier because you don't get nice cancellation from the direction orthogonal to the loop that you've picked.
But if you do one boundary and the other boundary orthogonal together.
No, because you're say you pick it here, yeah, and say you pick this one here.
Yeah.
Right. There's still whole bunches of your Brillouin zone that you've never touched.
Yeah, but according to your logic, they should all cancel out with each other.
They should all cancel, but you need to measure all of them.
Oh, okay. Okay. And then the next slide, what exactly does this colorful
okay, so this comes with some error, yes?
What is mu?
So mu is, so in the chiral PUF superconductor, that's our parameter that we're changing to control topology.
That changes your topology,
yes.
Right?
Yes.
And then.
So if you have a perfect quantum computer or a very good one, then your gate error sits down here. You get everything right almost all of the time. And what we're plotting is the ratio. So, you do this many, many, many times. And you see how many times do you get the Chern number wrong?
But why do you draw a line at 0.008?
Because this is our sort of effective maximal error that you can have before you start getting the Chern number wrong.
But how do you know about this number?
We looked at this plot and said, okay, well, this is the sort of minimum thing you got to have. We don't.
No, you don't know a priori, right?
You don't know a priori. No, that's a line that we put on after we computed this for increasing gate error. So we cranked up the gate error and found this is empirically the minimum.
Okay. Okay, then what exactly is topologically protected? And a little bit.
So what we're looking for effectively is, so your wave function has to change either by 0 times 2 pi or 1 times 2 pi.
Yeah.
Yes. So what we're looking for is the number of times that I go off of the principal branch of my logarithm. Because that indicates that I've gone around. Yes. Now it's possible that because of errors in one plaquette, I go across the principal branch, but in the neighboring plaquette, I will come back. So what we do is for each plaquette, we count, have we gone off the principal branch? Sometimes it goes, sometimes it doesn't go, but the net number will add up to either 0 or it'll add up to 2 pi or to 4 pi. So that is what we count.
But then you don't have error, right? Why do you have error?
Well, because at a certain point, your error becomes so bad that, I might go over twice or something else might happen that it just doesn't work anymore.
Okay.
Right? The numbers you get are not sensible anymore. And that's where this happens.
Then your previous slide that everything falls perfectly on 0 or 1 is actually ideal situation, right?
Yep. But there were days on the quantum computer where this did not work.
Okay. So some days it works.
Yeah, some days this worked, and there are other days where this did not work.
Just like the weather in Rio de Janeiro. So
yes,
make sure you pick the right time to visit. Right.
I will ask you in advance. But yes, there are days where just, all of a sudden the exact same calculations didn't produce the correct result anymore.
Okay. Okay, I think I talked too much. So I should, does anyone else have more questions? I'm sure some students will have a lot of questions.
I have a question. So let me try to summarize what I understood, and you tell me if I understood what you said or not.
Sounds good.
So usually people talk about topology in quantum computing as a way of avoiding decoherence. So you want to make a topologically protected state that both errors can't affect the thing.
Yep.
And then you can make your quantum computing with those states, like logical qubits.
Yes.
But what you're saying is very nice because it's different. Because what you're saying is you want to take a system that you want to know something about, and you measure observables, which will tell you something about your system, but the results of those measurements are not affected by the noise that your quantum computer is subject to, and you will still get the information that you want. So it's a little bit of a twist, no, in the topology.
Yeah, no, it is. And actually, we've run into problems with this because the moment you mention topology and quantum computing,
everybody goes that way, right?
Everybody immediately goes to topological quantum computing and error correction and this and that. And this has nothing to do with error correction in the same way. Okay. Rather, we use the inherent topology of the physical model that I care about to produce something that is protected against noise, rather than trying to like use topology to correct the error in my qubits. So yes, you have it entirely correct.
So it's like you're looking at robust observables that will give you information about what you want.
Yep.
This is very nice.
Thank you.
Cool. Okay. I just wanted to see if I.
Yeah, no, you got it.
Okay, thanks.
In fact, that's almost the title of the paper. Where did they go? Robust measurement of wave function topology.
Okay, I didn't see.
No, you're good.
Any other questions? And I will ask another one. So you use chiral P-wave, which is a 2x2 model. Yep. What if you have, let's say, 4x4, like sometimes it's symmetric? What will be different here? Other than just, your Hilbert space is larger, maybe, right?
I think nothing other than the fact that your Hilbert space is larger. We've done this also for the ensemble geometric phase. So for, finite temperature states, we've done this for the 2/3 filled Haldane model. So we've done this.
Yeah, well, let me put it this way. Because in different, I should say me and Gero are working on this pretty much now. Because if you go to a different kind of systems, I'm not sure this Berry curvature, or maybe you have to find some other ways to define your Berry curvature, right? So yeah, maybe we can think about, maybe we can discuss if you wanted to, generalize to some other systems, right?
Yep.
Actually, you might be able to, let's say, do some synthetic higher dimensional topological insulators that does not exist in reality. Right?
Yes.
But in this way, you might need to find a different definition of your curve.
So as long as you're working with gapped systems, it is fine.
Now, for instance, if you go to 3D, then you can imagine it's not a loop anymore. It's got this other object, right? So then you got to figure out how you.
But then why not? Then I'm on a 3 torus, and that's not the same.
Well, I'm not sure it's that simple that you can just say you construct loops this way, loops the other way, and then just cancel it out. Maybe
no. So
right?
the cancellation happens when you do a full integration over your Abelian zone.
Yeah, right. But I mean, how you define your local loop? I mean, here your loop is this U. But
yeah, then you have to do a 3
dimension.
Yes.
Probably.
Yes.
You can change.
Well, this is a good point. What do you have to do? This is a good question.
Yeah, you have to resort to our recent work. Yeah, so we can discuss about it.
Good, we should. Yeah, no, that would be interesting because I've only really seen this technique applied in 2D.
Yes, right.
Yeah.
So in 3D, then, actually, I don't really have an answer either. But I mean, something very similar.
Yeah, I don't know. Yeah, okay. We should talk about it.
Right. We should talk about a lot of things, right?
2 more weeks, then my semester is over, and then my brain will.
Oh, me too, actually. Okay, then maybe we can discuss more in December, right?
There you go. December would be great.
Okay. Do we have any other questions from the audience? Okay, if not, then I think we should thank Lex for this very nice introduction of both, let's say, the fundamental aspects of quantum computers and also what he has done recently, right? Very interesting.
Thank you for having me. It's been a lot of fun. I appreciate it.
Yeah, very nice.
Great.
Okay, cool. So let's exchange some emails for some further discussions.
Sounds good. And if anybody has further questions, I'm happy to answer questions via email about, basics of quantum circuits. I can send you the ones we ran. It's all fine. It's all public.
Okay, sounds very good. Okay,
All
thanks
right.
a lot, Lex. Yeah.
Cheers, everyone. Bye.
See you later.